Uh, so this question is about this equilibrium that's going on, right? PCl5 reacting with in equilibrium with PCl3 and Cl2. So the first one is the equilibrium pressure inside the syringe, and he's saying that this thing is in equilibrium. The equilibrium pressure inside the syringe will be greater than the atmospheric pressure. Uh, it's not going to be, because if the pressure inside is greater compared to the atmospheric pressure that's pushing from the outside, the plunger would start moving out, or it's going to come out. So the equilibrium pressure inside the syringe would probably be equal to the pressure that's coming from the outside. So the first statement is wrong. Then he's saying when the plunger is pushed in, the equilibrium adjusts to produce more PCl5. So when you push the plunger in, what are you doing? Are you increasing pressure or decreasing pressure?
Decreasing.
When you push the plunger in, that's an increase in pressure. So where would the equilibrium shift, forward or backward, if you increase pressure? Less gas or more gas? What's the Lee Shadler?
Forward.
If you remember, when you increase pressure, when you try to increase pressure, you try to push it in, the amount of gas is going to decrease. Because the volume would decrease, so less gas would be produced. So less gas mole side is favored, and that's going to be the backward reaction. It's going to go in the backward direction. So the equilibrium is going to adjust to produce more PCl5, and that is true, because in the forward side there's two Cl2 gas there are two molecules of gas. On the backward side there's only one. So if you push the plunger in, you increase pressure and less gas would be produced, which is this side. Is this clear? Okay, Anna, Kausa, Mariam, is this clear?
Yes.
Anyways,
Yes.
okay, the volume of gas in the syringe at equilibrium will be greater than if no dissociation had occurred. So if no dissociation had occurred, if you just had PCl5, then obviously the volume would be lesser. If it had dissociated, the volume of gas would increase, because that one molecule is now turning into two molecules. So this statement is also correct, that the volume of gas at equilibrium will be greater compared to if no dissociation had occurred. So if this molecule had not dissociated, which means that if it had not broken down, the amount of gas would have been lesser. If there was only PCl5, the amount of gas would be lesser. If PCl5 breaks down, decomposes, the amount of gas is going to be much more. So that's for this one. Let's just move on, see if there's some other question. For example, this one. Let's try and do this. Which change of conditions will cause the purple color of the equilibrium mixture to become paler? So there's purple over here, and you want it to be less purple. You want it to become paler. That means what you're trying to do is you're trying to move it or push it in the forward direction. You want to make it colorless. So where would a change in pressure, if you decrease pressure, which side would be favored? More gas or less gas? What's the Lee-Shatler principle?
Less gas.
If you decrease pressure, it's more gas. It's always more gas. Decreased pressure means that you're expanding the volume. It's always more gas would be produced. And vice versa, if you increase pressure, the rule is that more gas mole side is favored. And the other one is, if you increase in pressure, you're compressing it, less gas would be produced, less gas mole side would be favored. But in this specific case, both sides you have the same moles of gas. Like if the reaction moves forward, you get how many moles of gas? You get 2 moles of gas. If the reaction moves backwards and H2 and I2 are produced, you still get 2 moles of gas. So in this case, pressure is not going to have any effect at all. No matter you increase or decrease pressure, there is no less gas side and there is no more gas side. It's going to remain exactly where it is. Okay, is this clear?
Yes. Yes.
So next one. Remember, I want to make it paler. I want to make it colorless. Should I decrease temperature or increase temperature? The forward reaction is endothermic. So would a higher temperature favor it, or would a lower temperature favor that?
Increase temperature.
Okay, so it's going to be increased temperature. Increased temperature favors endothermic reactions, and it was an endothermic reaction. I mean, the forward reaction was the endothermic reaction. Enthalpy changes are always given for the forward reaction. So let's just quickly go through and see if I'm just going to quickly do this. So there's this equilibrium reaction. Is saying which one is not correct. If you increase pressure, less gas mole side is going to be favored. So which side has less gas? You've got two molecules over here. You've got in the backward side, if the reaction goes backward, it produces three molecules. So less gas is the forward side. If the reaction moves forward, three molecules of gas turn into two molecules of gas. The amount of gas decreases. So you get more SO3. You get a higher yield of SO3. So that statement is correct. The next one is increased temperature gives a higher yield. Whenever you increase temperature, which reaction is favored? It's going to be the endothermic. Now, delta H is given as negative over here. So that means the forward is exo, and the backward one is the one that's going to be endothermic. So when you increase temperature, the endothermic reaction is going to speed up, which is going to be this one. It's going to go in the backward direction. So the amount of SO3 would decrease. It's not going to be a higher yield, and that's basically your answer, the incorrect statement. All the other ones are correct. The forward reaction oxidation state of sulfur changes from +4 to +6. So it is +4 over here, and in the forward direction, it becomes +6. And vanadium pentoxide is a catalyst, and that's, if you know contact process, it is a catalyst. So let's do this one. This is about partial pressure, so we can ignore that for now. Just let's attempt this question. So remember that increased temperature is favors endothermic, and decreasing temperature, you decrease the temperature, you make it cooler, it favors the exothermic reaction. So you've got this reaction going on. You don't know which one is the endothermic reaction, you don't know which one is the exothermic reaction. So you have no idea whether the forward is endo or the backward is the one that's endo. So you have no idea which one is endo, which one is exo. But instead, they've given you a table, and in that table, what he's doing is he's increasing the temperature. Now, we know that if you increase temperature, which reaction would be favored? The endothermic reaction. Right? The endothermic, whichever the endothermic reaction is. We have no idea which one is the endothermic, but the endothermic reaction will be favored. Now, look at the change in concentrations that are happening. At 230 degrees centigrade, the equilibrium had the concentration of NOCl, NONCl2 are all given. When you increase temperature, the concentration changes, and those are also given. So can you tell me, when you increase temperature, by looking at the concentration, is it favoring the forward reaction or is it favoring the backward reaction? Can anyone answer this? Qasim, Mayim, Nabila, Aisha? What's happening to the Anna? Can you answer this? Okay, what's happening? Where is the equilibrium shifting by just looking at the concentrations?
Forward, I guess.
Okay, because if you look at NOCl, NOCl had a higher concentration. But when you increase temperature, now NaCl has a concentration that's 10 to the power minus 4. So that means the amount of NaCl decreased when you increase temperature. That means the forward reaction is happening. That the amount of NaCl is decreasing and the amount of NoNCl2 is increasing. Like NO was lesser, it was 1.46. Now it's 7.63. So that means it's almost 5 times more. This was 1.15. Okay, so the amount of NO is increasing. Now, by looking at it, the NoCl concentration is decreasing and the NO concentration is increasing. So is the forward reaction endothermic or exothermic? Achha, this question, because we haven't studied Kc, this question specifically involves Kc as well. So we're going to come back to this question later on as well. But by just looking at the concentrations, NoCl is decreasing and the NO amount is increasing. I would suspect that the forward reaction is speeding up. So if you increase temperature, which reaction speeds up? It's going to be the endothermic. So that means the forward reaction is the endothermic reaction. Remember, we just made a guess right now. Okay, because this question involves Kc. We haven't done Kc. So we're going to come back to this question, but I just made a rough guess about what's happening, that the forward reaction is, by looking at the concentration, the forward reaction is speeding up. And whenever you increase temperature, the endothermic reaction speeds up. Is this clear?
Yes.
Okay.
Yes.
And remember, we didn't fully answer this question yet, okay, because this involves Kc as well. So we're going to start with Kc now. Okay, and then we'll be able to figure out what the technical way to answer that question is. So what's the equilibrium constant Kc? Now, Kc is simply the concentration of the products and divided by the concentration of the reactants. Like whenever you have an equilibrium, you have reactants turning into products, and you've got products that are turning back into reactants. But the concentration remains constant, because if every second 100 molecules of P products are formed, and every second 100 molecules of product turn back into reactants, the amount of product remains constant. There's no net increase or decrease in the amount of products or reactants. So the concentration becomes constant. Uh, but the equilibrium position could vary. Like at equilibrium, you could have a lot of products and you could have very few reactants, right? So that means the equilibrium is favoring the products. So it's a ratio. It's the ratio of the concentration of the products with respect to the ratio of the reactants. So the equilibrium could favor, if it favors products. So it depends on the conditions, what side it favors. Like if like the bottle, that bottle reaction, right? I told you that the concentration is the bottle reaction. So I told you that the concentration of the particles becomes constant. But if you change conditions, like if you take this to a very high temperature, there would be a lot more water vapors formed, and there would be a lot lesser liquid water. If you take it to a very low temperature, like to 10 degrees centigrade, very low temperature, put it in a fridge, the amount of water vapors is going to be very less, and the amount of liquid is going to be high. So the equilibrium could move forward or backward. But if equilibrium is reached, the quantity would not change. So in this case, if equilibrium favors products, then Kc has a high value. And Kc would specifically be greater than 1. Like if you have more products compared to reactants, then obviously Kc is like, if you have 10 and this is 5, you've got 10 products and you've got 5 reactants at equilibrium, then Kc will have a positive value, will have a value that's going to be greater than 1. And vice versa. The equilibrium could favor the reactants as well. So if under the conditions, the equilibrium, it favors your reactants. then that would indicate that Kc has a low value, as a small value. And it's probably going to be less than 1. It's going to be in decimals. Like if you have a lot of reactants at equilibrium, you've got 10 reactants and you've got 5 products, then it's going to be 0.5. So it's going to be in decimals. So is this clear?
Yes.
One thing you should remember about this is that you always it's always concentration of the reactants and products. Like when you're calculating Kc, it's always the concentration. And what did I tell you about concentration? I told you that the term concentration, it only applies to solutions or gases only. ठीक है, that's where concentration, where you use the term concentration. Like if you have a beaker, what does the term concentration actually refer to? It refers to how close the particles are. Like if you have a solution, and in the solution you have two solutions that have equal volumes. One has more particles. So it's not even about the quantity of particles. It's so one of them has more particles, the other one has fewer particles, right? So it's not really about the volume of the particles, the volume of the solution. It's not about the number of particles of the or the total number of particles. It's how close the particles are. That is what concentration is. This has a higher concentration. If I decrease the volume, it will still have a higher concentration. Like if I remove some of the water, I pour some of it off, the level decreases, right? The volume could change, but the concentration doesn't change. It still has a higher concentration. You can even decrease the number of particles, and it would still have a higher concentration. Like I can decrease the number of particles, but if I simultaneously decrease the volume as well, like if I simultaneously decrease the volume as well, the particles are still closer together, so that's more concentrated. So remember what concentration actually means. Concentration means how close together are the particles, or how far apart are the particles. Like how it's a measure of the closeness of the particles. So it's not a measure of the volume, it's not the measure of the amount of particles, it's how close together they are. And that's also true for gases. Like in gases concentration term would also apply to gases. Like gases can be close together, they can be far apart. Like now gases can move freely, so obviously so in gases the particles could be very far apart, or the particles could be very close together. So that's more concentrated. Okay, is this idea clear?
Yes.
So that is what concentration is. And remember, solids are always going to be having constant concentration. Okay, the term concentration does not apply to a solid. And it's always going to be taken as 1 or a constant, because the concept of being close together or being far apart, that is not going to happen for solids, because solids, this is what a solid would look like. They're always close together. So you've got your solids, and we'll just pick this. Just 1 second. So the term concentration is never going to be applied to a solid, because solid it doesn't change. Its concentration doesn't change. The closeness or the spacing between them, it never changes. They are always tightly packed. And I did one thing, which was that when you're trying to calculate Kc, ठीक है, and there's a solid, and you have to. So if you're trying to calculate Kc and there's a solid, you're going to put it as 1. ठीक है, the concentration is going to be taken as a constant. Similarly, what else did I tell you? Whose concentration is going to be constant? Anything which is present in large excess. Would have constant concentration or almost constant concentration. Um, so anything which is in large excess, one example is water in aqueous solutions. Because there's so many of them that their concentration would almost be a constant. So I'll just quickly show. So for example, if you have a reaction going on and there are two particles that are reacting, one of them is the red one, like the two gas particles reacting, and the other one is are the blue ones, and they react in 1:1. Now the blue ones are in large excess, which means there are a lot of them. So there are lots of them. So if one of the red molecules reacts with the blue ones and they react to produce some product, let's make it a so that's your product. So what happened to the concentration of the red particles? It decreased by 1. It decreased by 50%. Like now the red particles are quite less constant. There's only one red particle in the entire container. So it's very far away from all the other red particles because there are no red particles anymore. But did the spacing between the blue particles change by much? It didn't change by much. The concentration of the blue particles is kind of exactly the same. And if any of the red particles again reacts with the blue one, the concentration of the red particles would go to 0. But the spacing between the blue particles, it's hardly changing. So if something is in large excess, its concentration kind of doesn't really change much. So keep that in mind, that anything that's in large excess, its concentration would also be taken as 1. Is this clear?
Yes.
So solids would be taken as 1, and anything that's in excess, like water in aqueous solutions, that's going to be taken as 1. So the very first thing is you'll be asked to write expressions for Kc. And you'll be asked to expressions of Kc, and you'll be asked to find units as well. That's the first part that they're going to make you do. So how do you write the expression? So you have a reaction, and also remember Kc it's only calculated if the reaction is at equilibrium. Like if the forward reaction and the backward reaction have equal rates, only then can you only calculate it for reactions which are at equilibrium. So the values that you're going to input in when you're trying to calculate Kc is you're going to use the concentration of the reactants and the products, but it's going to be the concentration that's present at equilibrium. The equilibrium has to be attained. Only then can you calculate Kc. So you have this reaction N2 reacting with H2 and it's in equilibrium with 2NH3. That's the Haber process. So the first thing is Kc. What did I tell you Kc was? It was the product concentration divided by the reactant concentration, right? Now in this case, my product, in this particular case, My product is NH3. So it's going to be NH3 concentration divided by my reactant concentration. My reactants are going to be, these are my reactants. So that's my product and that's my reactant. So my reactants are N2 concentration, and my reactants, their concentrations, they must be multiplied by the H2 concentration. So the two things, they have to be multiplied. A lot of people put a plus sign over there. So it's going to be products divided by the reactants. And you have to do one more thing, and that is that the coefficient in the equation becomes the exponent. It's going to become the exponent. Because if you have two NH3s, so it's going to be, you can either write NH3 twice, but that would become NH3 squared anyways. And my reactants are N2 plus H2, they 3 times H2. So it's N2 plus H2 plus H2 plus H2. So if you write H2 3 times, it would automatically become H2 cubed. So whatever the coefficient that's present over here, it's going to become the exponent. And that's going to be my expression for Kc in this particular case. So that's one equation. Is this clear?
Yes.
Just similarly, you've got, let's do another one. We've got SO2 plus half O2 in equilibrium with 2SO3. Not 2SO3, just SO3. And they're all gases. So how would you write the expression for Kc in this case? It's going to be products. The products are SO3 concentration. The power is going to be 1. You don't have to write 1. Divided by the concentration of the reactants. My reactants are SO2. And concentration, remember, is represented by these square brackets. And the other reactant is O2. They're both going to be multiplied. Anyways, SO2 is 1, so you raise it to the power 1. O2 has a coefficient of half, that means you raise it to the power half. That's basically under root. So that's going to be your expression for Kc in this case. Clear? Is this clear?
Yes.
As the next thing, you'll be asked to find units. How do you find units? Units are, just like in physics, in homogeneous equations, the units are going to be that the top one. So we're going to try and find units. Because you're putting in concentration, concentration has a unit which is mole per dm cube. So it's going to be mole per dm cube, and it's going to be squared, right? The top is squared. The bottom part is mole per dm cube, that's N2, multiplied by, again, H2 cubed. So that's its concentration, mole per dm cube and mole per dm cube, and that's going to be cubed. Now, so that's, you simplify this and you find the unit. Now, finding units in this way it's not that difficult. It's easy, but it's time consuming, and there are chances of a lot of mistakes when you're trying to simplify this. The easier method is just take x as mole per dm cube. Okay, so assume that mole per dm cube is x. So it's x squared divided by x into x cubed. What do you get? If you simplify this, it gives you x minus 2. And then what you can do is you can input or replace x with mole per dm cube. So it's mole per dm cube and the power is minus 2. And you can then solve this. It's going to become, mole would become minus 2 and dm would become 6. So is this clear?
Yes.
Yes.
So I mean, you can either use mole per dm cube and simplify, but it's going to consume a lot of time, and there are chances of making a lot of mistakes. Like you would have to open the bracket, and dm would become minus 9, and then it would multiply by another dm minus 3, and that would become, even I don't know what that would become. It's dm minus 12 something. So a lot better would be just take concentration as x, simplify, you get something in x, you just put what x is. X is mole per dm cube. We're going to try and do the same thing for this one. So it's x power 1. X is mole per dm cube. X power 1 multiplied by x to the power half. What do you get? The x would get cancelled out. It would become x to the power minus half. So that's mole per dm cube. And the power is minus half. And if you open this up, it's going to become mole minus half. And dm would become plus 3 by 2. So that's going to be your unit in this case. So we've done 2 questions related to this. Is this clear? Ahmed, Anna, is this clear?
Yes.
Okay, so we're just doing the expression. Remember that, so I'm just going to recap this. Remember that when an equilibrium is reached, the amount of products and the amount of reactants, they become constant. They don't become equal, but they become constant. They don't change. So the ratio of the products versus reactants, that's going to give you a constant value. And this value of Kc, it's always a constant. It's always a constant. It only changes with temperature. So I'm going to write that as well, that the Kc value. So every equilibrium has this constant. It has this equilibrium constant. It always tries to maintain a ratio. Like if you have water in a water bottle, there's a small amount of water vapors forming. There's liquid water. There's a ratio that exists between them, and that ratio is always a constant. Anyway, so Kc is always a constant. And it only changes with one thing, and that is with temperature. Make sure you remember this because you get a lot of MCQ questions and lots of small questions where they ask you what's going to change the value of Kc. That's going to be temperature. For example, where's the water example? Only temperature would alter the position of the equilibrium or change the, like this one, this water equilibrium, right? The amount, the ratio of the vapors and the ratio of the liquid water, that's always going to be a constant. Even if you try to remove the water vapors, right? If you try to remove all the water vapors, you go inside, you open the container, you remove all the water vapors. Condensation would immediately stop, but evaporation would continue to happen. And when that evaporation happens, more water molecules would automatically be produced. So you can see that it's trying to maintain that ratio. It's the amount of water vapors and the amount of liquid water, that ratio is maintained. Is this idea clear? Okay. Even if you try to disturb the equilibrium, that ratio between products and reactants, that's always going to be maintained. Okay. Emma, is this clear? Anna? Mariam, is this clear?
Yes.
Yes, sir.
Now, there's only one thing that changes that, and that is temperature. Like if I really increase the temperature, then if I really increase the temperature, there would be continuous evaporation that's going to happen. If I really increase the temperature, take it to a very high temperature, then there's going to be a lot of water vapors formed. And then you can see that all of a sudden that ratio is now changed. Okay, the amount of products now is a lot more, and the amount of reactants that they're going to decrease. If I really take the temperature to a very high temperature, like 1000 degrees centigrade, then there's not going to be any liquid water left. You'll just have products. There would only be products, and the amount of reactants would be very, very less. So only temperature is going to alter this ratio. So is this clear, everyone? Aisha, Alicia, is this clear?
Yes, sir.
Yes.
So coming back to this ratio, products to reactants, always a constant. Even if you alter the conditions, the ratio of the products and the reactants, the equilibrium automatically shifts in either forward or backward direction to maintain that ratio. but not with temperature. If you change temperature, the entire equilibrium either moves to one direction or it moves to the other direction. So that's what KC is. Try and I'm going to give you some questions. Try and do those questions now. Try and write the expressions. For example, you've got 2NO2 in equilibrium with NO, right? Find the you're supposed to find the expression of KC and also the unit, both. You've got HCl in equilibrium with H2 and Cl2. Number 3 is let's do let's do this one. So I've got P4O10 and it's in equilibrium with and let's assume all of them are gases. So there's 4P and there's 5. It's not Cl2. There is no Cl2. So there's O2 and there are 5 of them. Yep, okay, that's fine. We did the NH3 one. We can do CH3OH and it's in equilibrium with CO plus H2O. There's going to be 2 H2Os and there's going to be 1 CO. So you would need how many oxygens? There's 1 over there. So you would need the 4 over here. So that you would need 1.5 oxygens, 3 by 2 oxygens, I think. I just made that up. Is this equation balanced? 4H, 4H, 1O. You had 5 oxygens on this side. So there would be 2 O2s. So there are going to be 2 O2 molecules. So find the expression and the unit. This is a very basic step, but this is one of the most important steps because if you get that wrong, so I'm just going to post it in the classroom. So try. I'm going to post it in the group as well. Try and solve this and. And I'm posting it in the classroom as well. Do upload your answers over there. Is this clear? Anyone any questions? Is this fine?
Yes, sir.
Yes, it's clear.
Let's continue tomorrow then. I'll just post the classroom link as well. Okay then, everyone. Take care. Allah Hafiz.
Allah Hafiz.